Hello and welcome to another video of Grokking the Coding Interviews series. My name is Parth and we are going through the best first search pattern. And in this video, we'll have a look at reverse level order traversal, which is classified as an easy problem. In the previous video, we had a look at the normal level order traversal. So let's go ahead and see how we can obtain the reverse order for the level by level traversal. Essentially, what we want to accomplish here is we have a binary tree that's shown in the screen, and what we want to return is we want to return a level by level traversal, but in reverse order, like order. So the first level will be returned at the end of this array, and the second level will again retain its position. The final level will be the first array in the result array, which we'll have at the end. So we have an understanding. I think probably the way I'm thinking of approaching it, our approach will remain exactly the same as the previous implementation. Just simply either we can say reverse the list while we are returning the result array, or we also have an option of append left for a list. So we can simply append the results left side, and then we'll have the reverse order which we are looking for. So let's quickly try to implement and see if things are working fine. And here, if you see, we use DQ, and DQ has an option where we have append left. You wouldn't be able to run this operation on a usual list. So if the root is none, we simply return result. We do not need to do any traversal. We want the queue, which will be the DQ. We want to append the root into the queue, and we want to iterate over this queue until it is empty. At each level traversal, we want the level size, which will be length of the queue. We want the level nodes, which will be the nodes present at that level. This will be a list. And essentially at this point, we want to iterate, or we want to pop the left element's level size times. So in range, level size, current node is q dot pop left, and level nodes dot append current node dot value. Okay, and at this point, we want to see if the current node has a left child. If it has a left child, we'll push it into the queue. We check if the current node has a right child. If it has a right child, we push it into the queue. And here is where we do the magic. So in result, we go and say append left if I'm getting the naming convention right. So if we had to remove the leftmost element, we did the operation which was pop, and then we specified left. I'm expecting the append left would work the same way. Result append left and level nodes. And this should actually give us the response we are looking for. So let's quickly go through the implementation and see if it makes sense. We have if the tree is empty, we simply return the result. We do not need to do any traversal. We get a queue, append the root. While the queue is not empty, we keep iterating. We get the level statistics, which is the size and nodes. We iterate, we pop the level size elements from the queue. We append the current node's value into the level node. If it has a left child or the right child, we append it into the queue. Append is not spelled correctly. And the result we append in a peculiar manner where we want to append to the left side of the result queue in order to get the reverse order. And once we have that, we simply go ahead and return the result. It should give us the answer we are looking for. Let's try to run and see if we have made any errors. If we have not, we'll have the correct answer. 9, 10, 5, 7, 1, 12. 9, 10, 5, 7, 1, 12. So it seems like our implementation is working. Let's quickly speak about the space and time complexity of this implementation. The runtime complexity from where I see it is O of n. We are traversing all the elements once. The space complexity in the queue, we can at most keep n by 2 elements, so it'll be n of n, and we are also returning a queue which is result. But I'm not sure if this left append left operation is expensive. So from what I see, the space operation is also O of n and runtime is O of n, but I would like to see if I'm missing out something on append left. So let's quickly do a check here and see in case we are missing anything. The time complexity O of n, we were right about that, and the space complexity again is O of n. There are no surprises. I hope you like the explanation clear enough. Please let me know in case there are questions. If something was not clear, I'll be more than happy to improve. Until the next video, have a great day.